If you'll recall, when we studied integration, we looked at certain categories of integrands. If we could determine the nature and category of the integrand, then we could associate it with a certain process for finding the antiderivative. In the same way, we can study categories of series. At this point, we've already identified the geometric series and telescoping series. For those two series, we had a specific way that we found the sum. In general, we know that the sum of a series is the limit of the sequence of partial sums. But geometric series and telescoping series are fairly simple to sum. Our focus in section 9.4 is going to change just a bit. Instead of attempting to sum the series, we're just going to answer the question, does the series converge or diverge? And we're going to look at a variety of tests that help us to answer that question. In section 9.4, we will examine the divergence test, the integral test, and p-series. In this video, we'll examine the divergence test. Let's begin with a specific distinction. Recall that if the limit as n approaches infinity of the sequence a sub n, if that's equal to L and L is finite, then the sequence, which we denote with a set of curly braces, a sub n, converges to L. So if the limit of a sequence is finite, then the sequence converges. And it converges to L. So we not only know that it converges, but we know what it converges to. And once again, let me reiterate, we're talking about a sequence here. Now specifically, if the limit as n approaches infinity of the sequence is 0, then we can conclude the sequence converges, and we can conclude that it converges to 0. This all works very nicely when applied to sequences. However, when we get into the territory of a series, which of course is the sum of that sequence, things get a little bit muddier. So to introduce the divergence test, I want to talk to you a little bit about logical connectives. Let's go through a quick logic crash course in preparation for understanding the divergence test. In your math classes, in your textbooks, you've probably read a lot of statements of the form, if something, then conclusion, right? That's called a conditional statement. This conditional statement can be written in symbolic form where the one direction arrow represents the conditional. We read that statement, if P, then Q. P is called the hypothesis of the conditional, and Q is called the conclusion. So if the facts stated in the hypothesis can be established, then Q, that quality or condition, is the natural outcome or conclusion of that hypothesis. If P, then Q. This is called a conditional statement. For example, if I live in Amarillo, then I am a Texan. The connectives here are the words if, then. I live in Amarillo is the hypothesis of the conditional. We can call that P. I am a Texan. That is the natural conclusion from that hypothesis P. Now, I want you to observe this happens to be a true statement. If I live in Amarillo, then I am a Texan. Now, there are three other variations of this conditional that are related. The first one is called the converse. The converse simply reverses the direction of the conditional. Notice we've switched the position of the conclusion and the hypothesis. Now, Q is the hypothesis and P is the conclusion. So if I apply this pattern to our original conditional, we can see here my connective words, if, then. I am a Texan. That was the previous conclusion. Now it's in the place of the hypothesis. And the conclusion or result is P. If I am a Texan, then I live in Amarillo. Now think about that statement for a minute. Do you think that's true? Always, if I am a Texan, then I live in Amarillo. No, I might live in Dallas, for example, but I would still be a Texan. So we can make the observation that this is a false statement. It's important to recognize here that because these two variations of the conditional do not have the same truth value, they are not equivalent statements. So the symbolic form of the conditional, the one-way street arrow indicates that I can only read that conditional in one direction. Let's consider a couple other variations of our original conditional. The next one is called the inverse. Now, the little squiggle that you see here represents a negation. So the negation of a statement has the opposite truth value of the original statement. So I could read this, if not P, then not Q. Notice the statements P and Q are in the same order as the original conditional, but they have both been negated. If we apply this pattern to our original conditional, it would sound something like this. If I do not live in Amarillo, then I am not a Texan. So the words if and then are logical connectives. Not, the negation, is also a connective. And the hypothesis and conclusion are in the same order as the original conditional. But listen to the statement again. If I do not live in Amarillo, then I am not a Texan. Is that always true? Again, we could cite the situation where you live in Dallas, you are still a Texan. So we could make the observation that, again, this is a false statement. Let's look at one more variation, and then I'll show you how this is going to apply to the divergence test. The last one is called the contrapositive. Notice we've got the squiggles again, that represents the negation, and we are dealing with a conditional statement, a statement of the form if P then Q. And notice the order of our statements. Q is first, P is second. That's the opposite order of the original conditional. If we apply this contrapositive pattern to the original conditional, it would read something like this. If I am not a Texan, then I do not live in Amarillo. Again, the connectives are if, then, and not. And we have the statement not Q implies not P. And once again, observe it's the opposite of the original statements in the previous conditional. So what do you think? Listen to the statement again. If I am not a Texan, then I do not live in Amarillo. Is that true or false? Well, that's true. If you're not a Texan, then that excludes the possibility that you could live in Amarillo. So of the variations that we've considered here, we can observe that the conditional is equivalent to the contrapositive. In addition, the converse and the inverse are logically equivalent statements. So make a close observation here. The conditional has the order P then Q, if P then Q. The equivalent statement, the contrapositive, has the opposite order. Q is first, P is second, and both of them have been negated. A conditional is equivalent to its contrapositive. So we will examine the contrapositive of a conditional statement here, and that's the form that we're going to use in practice. Now also notice the relationship between the converse and the inverse. Notice that the order of the statements has been reversed, and in the inverse, both statements have been negated. So the relationship that a conditional and a contrapositive has, that is, the statements have been reversed and both have been negated, that's the same relationship that the converse and the inverse has. The order of the statements has been reversed and both of them have been negated. So if you really want to get fancy, you could say that the inverse is the contrapositive of the converse. So what in the world does any of this have to do with the divergence test? Well, we're going to take the conditional and its contrapositive pattern along with this special note and apply both of those tenets to understand the divergence test. Here's the theorem for the divergence test. If the series, notice we've gone from sequence now to series. If the series from k equals 0 to infinity of a sub k converges, then the limit as k approaches infinity of a sub k equals 0. Remember I told you at the beginning of this section, our goal is to determine if a series converges or diverges. Notice the hypothesis of this conditional is that it converges. So in order to apply this theorem directly, I would have to know initially that the series I'm examining converges. If that's true, then the natural conclusion or result is that the limit as k approaches infinity of a sub k equals 0. we have learned that this is not equivalent to the converse. The converse would sound something like this. If the limit as k approaches infinity of a sub k equals 0, then the series k equals 0 to infinity of a sub k converges. So this is the danger that I'm putting so much energy into explaining to you. We want to be very careful that we do not read that in the form of the converse. That is, we don't want to say if the limit is 0, then the series converges. Go back and contrast that with this first point. If we're dealing with a sequence and we find out that the limit is 0, then yes, the sequence converges, and in particular it converges to 0. But the rules for sequences are not the same as the rules for series. So if the limit of the term of our series is equal to 0, then the series may or may not converge. So in practice, the contrapositive will save the day. Now remember, in the contrapositive, we're going to switch the order of our statements and negate both of them. So I'm going to, this statement is Q, this statement is P. I'm going to switch their order and negate them both to form the contrapositive. It's going to sound like this. If the limit as k approaches infinity of a sub k is not 0, this is not Q, then the series from k equals 0 to infinity of a sub k, remember I'm negating here, diverges. So the negation of converges is diverges. This is the format in which we want to apply the divergence test. If I find the limit of the term of the series and I discover the limit is different from 0, then my conclusion is that the series diverges. That's why this is called the divergence test. Note, if I find the limit as k approaches infinity of the term of the series and I discover it's equal to 0, right? It's not different from 0, it is 0, then the divergence test is inconclusive. It may or may not converge. I don't want to accidentally apply the converse. That is, if I find this, if the limit is 0, I do not want to conclude convergence because we know the converse is not equivalent to the original conditional. Got it? Does that make sense? So if we find the limit of the term of the series is different from 0, we conclude that the series diverges. If the limit is 0, the test is inconclusive, and we'll learn other tests that we can try in its place. So really, in practice, the contrapositive of our divergence conditional is really easy to apply. I just want you to learn a little something along the way and avoid the pitfall of mixing this up with the rules for sequences. So here we go. Example 1. Use the divergence test to determine if the following series diverge. So the only information that I can get out of the divergence test is divergence. Also note that the focus of these problems is not necessarily to sum the series anymore like we did with geometric or telescoping series. Now our focus is simply to determine, does the series converge or diverge? So looking at example A, we have the sum from n equals 0 to infinity of n squared. So I'm going to apply the divergence test. I'm going to find the limit as n goes to infinity of the nth term formula for the series. Well, the limit as n goes to infinity of n squared is infinity. Observe this is not equal to 0. So we can say by the divergence test, the series diverges. So I'm being specific with my conclusion statement here because as we add more tests, it will be important for us to cite which test we are applying to particular series. All right, so all that background work for a pretty easy problem. Let's try example B. The series from n equals 1 to infinity of n cubed plus n divided by n cubed minus 3n squared. To apply the divergence test, we're going to find the limit as n goes to infinity of n cubed plus n divided by n cubed minus 3n squared. Now, we've been practicing L'Hopital's rule a lot, and notice L'Hopital's rule would apply here. That is, we have the indeterminate form infinity over infinity, so we could apply derivatives to the top and the bottom until we calculated the limit. However, the shortcut is, and maybe you learned this in STEM college algebra, but if the degree of the top is equal to the degree of the bottom, then I'm simply going to form the ratio of leading coefficients to determine the limit. This is what L'Hopital's rule would yield. So once again, if the degrees of the numerator and denominator are equal, then the limit is the ratio of leading coefficients. In this case, 1 divided by 1 is equal to 1. Notice this is different from 0. Therefore, again, we could say, by the divergence test, the series diverges. Practice writing down your conclusion statement, quoting the test that you're using. That gives authority to your proof. Another thing that I want to point out here is that we're saying the series diverges. We're not attempting to, well, it diverges, so we couldn't sum it anyway. Let's look at example C. The series from k equals 1 to infinity of k divided by natural log of k. So we're going to apply our divergence test, the limit as k approaches infinity of k divided by natural log of k. Now, we're not dealing with a ratio of polynomials here, so we can't use the same shortcut that I mentioned on example B. We will have to apply L'Hopital's rule because we do have the form infinity over infinity here. So applying L'Hopital's rule, the derivative of the top is 1, the derivative of the bottom is 1 over k. When we simplify this complex fraction, we have the limit as k goes to infinity of k, which is infinity, obviously different from 0. Therefore, we can say once again, by the, I'm going to call it dt because I'm out of room, by the divergence test, the series diverges. All right, we're getting the same conclusion on all of these because remember, the divergence test can only be used to establish divergence. Let's try the last one, the sum from k equals 1 to infinity of k squared over 2 to the k. To apply the divergence test, we need to find the limit as k goes to infinity of k squared over 2 to the k. No shortcut is available on this one because we don't have the ratio of polynomials, but we do have the indeterminate form infinity over infinity. So we can go ahead and apply L'Hopital's rule. We have the limit as k goes to infinity. The derivative of the top is 2k. Now here's a pop quiz from chapter 7. What is the derivative of 2 to the k power? If you'll remember, we make a copy of the exponential and multiply by natural log of the base. At this point, we can still determine that we have the pattern infinity over infinity, so we need to apply L'Hopital's rule again. That will give us the limit as k goes to infinity. The derivative of the top is 2. The derivative of the bottom, I'm going to make a copy of the exponential, multiply by natural log of the base, but I've already got a natural log of 2 down there, so I'm just going to square it to represent both of those. Now we can determine the limit. Notice the denominator is increasing without bounds. It's going to infinity while the numerator is static, so the limit is 0. Now this is the one that you really got to watch out for. If your limit is 0, put your eyeballs over here, right? Limit of 0, you got to be careful with this one. Yikes. The temptation is to conclude, oh, the series converges. Because if this were a sequence, we found the limit of the sequence to be 0, we would say the sequence converges and it converges to 0. But we're not dealing with a sequence, we're dealing with a series. If we get the limit of the series is 0, then by the divergence test, we have nothing. We can't determine if it converges or diverges. So we can simply say The divergence test is inconclusive. The series may converge, it may diverge. So our answer is we don't know. We can simply say the divergence test is inconclusive. Later on, we'll learn for a series that looks something like this, the ratio test will help us to determine the behavior of that series. Okay, I hope this has been a helpful video. I hope you've learned the divergence test and a little bit of logic on top of that.